So thank you, everyone. I'm very pleased to be able to present so it's part research and it's part our packages I have been developing. So I've been working on mental health related diagnosis. We have a project on suicide prevention. I did this talk for the lab a few months ago, but for the demo, I wanted to do something more interactive. But so we can first have a look a bit at this presentation to talk about the problematic and about the project. So we're working with the Veterans Affairs hospitals, trying to help with suicide prevention for military veterans in particular, also with youth-related hospitals. And so it's with the CELEHS laboratory led by Professor Kai. So our idea is to do an app for clinicians, helping them to follow up on at-risk patients. In order to be able to do that, we want to discover relationships between clinical concepts. Our data is electronic health records. We want to do knowledge graphs, basically. A second important thing is to be able to show up the EHR notes that talk about some specific points that the clinicians would like to see, because one of the challenges they are facing is that patients will have maybe interviews every week, and that makes a lot of EHR notes. So they want to be able to have quick access to the ones that are relevant to their specific queries. And also we'd like to be able to share results between hospitals, so while still preserving patient confidentiality. So I'll start a bit with introduction, problematization, and after we'll go into the tutorial part with code. And so I'll try to not take too much time on this, but the Diagnostic and Statistical Manual of Mental Disorders is a very important book for clinicians. It lists all the diagnostic criteria for the different mental disorders. And so it's a very base and important document for psychiatrists. So I tried to look a bit about suicidal ideation in this book, because it's one of our main focus to be able to understand suicidality. So what we can see is that it appears throughout the book in many different diseases, in many different sections. For example, in schizophrenia, it's in suicide. There's a section called suicide risk. It also appears in PTSD, panic disorder. It can be a diagnostic criteria for major depressive episode. So it's quite a complex. It's not really a diagnosis in itself. It's more a symptom that, or a criteria for other diagnoses. In the DSM, they talk about the assessment measures. So how they measure when people, for example, psychosis, autism, and they talk a bit about the fact that we need intermediates between the diagnoses that exist. For example, schizoaffective is one that doesn't really fit into any strict definition of the diseases that are present. And they would also like to take into account the variation of features, severity, intensity, combinations of symptoms also for the ones that have the combinations. So this is what brings us to try to understand better how we could use multidimensionality to understand better the mental disorders. There's the second section in DSM. The first one is about all these symptoms and diagnostic criteria I was talking about. And the second one is possible evolutions of DSM. And suicidal behavior disorder is one that it's a proposed diagnosis for future research. So it may be incorporated in next versions of the DSM. Another related diagnosis that is not yet for clinical use, but that is under research, non-suicidal self-injury, which is quite close, but there is a differentiation between suicidal behavior and non-suicidal self-injury. I talked a bit about how it evolves. For example, PTSD first had 3 clusters, now there are 4. And here are some of the key points. So now we can get back into the tutorial part. So this is the repository I prepared. You can clone it if you want. Here's the abstract I submitted for RMAD. I basically have some codes that you can run in your own environment. If you use Docker, you can pull this image I prepared. Otherwise, using this file, you should be able to install all the packages we will be using. We'll start by exploring a bit Europe PMC. So I'll be showing how we can analyze scientific publications related to suicide. As I was saying, our project will be using EHR data, but we also train our NLP algorithms on scientific publications. So once we explored a bit what we can do with Europe PMC, we'll be working with a local database of several thousand scientific publications. So I prepared 2. There is one of 1,700 and one of 8,000. So in this tutorial, I'll be showing 1,700 to speed things up. But if you want on your side, you can try to reproduce with the 8,000. And so once you prepared your computing environment, here's the link to the Dropbox folder, which should look a bit like this. And in here you have some of the files that we will be recreating, but that you can download to skip some parts if needed. One of the important one, if you're not using Docker, would be to download this one. And you will need to unzip it. It's 7Z. So let's try to see if the demo gods are with us. So in my environment, I would use this Docker command, start it up. So this is the classic Docker, but we can use this line because it enables us to forward the X session and have the plots. So in the Docker image, we have already all those packages installed. So I was saying I wanted to show a bit first how this came to be. Using the Europe PMC package, we can do, for example, search in the title, give me publications that talk about suicidal ideation and that are open access. So this is detailed in the vignette of Europe PMC. So if we do this query, we can see 1,400 records found, returning 100. And with this function, Europe PMC ftext, we can download the full text of the publication. Here I'm doing head on it to just get the 6 first ones. And so once we have that, we can have a look. This is the XML file, but there is the tidypmc package that enables you to parse it. So it would look like this. It's a table data frame with the section, paragraph, sentence, and the text. So once we have this file, this would be the command using the Docker. Otherwise, you can replace their pass variable by your either your local directory where you save the file, or just I guess just let it's empty string should be okay if it's in your local folder. So this would show up the path of the file. This will take a few minutes. So what I did is that I downloaded all the files from EPMC. We have the FTP address here where you can find all the files. Because I wanted to be able to parse it locally rather than using Europe PMC. And so I created two databases. One was 20% approximately of the total publications I found. I was searching for the pattern suicide that could include benonyms of suicide and suicidal. So I extracted each article from XML, built a new XML file, and basically once you have that, you just have to add these two. This is the prefix string, and this is the append string, like in the first line and last line, you add to it. And this enables you to use the functions from tidypmc that this function is calling. So it basically recreates a similar XML file as the ones that you can download on the FTP, but this time containing only the publications relating to suicide. So while it's finishing up, I can start explaining what we're going to do. So we first want to process the text. We want to sanitize it slightly, but try to not do it too much because we're still in the exploration phase, but still enough for it to be fed to the text2vec R package, which is the one we're going to use to build the embeddings. So it's Word2vec is now a bit old with all the LLMs coming out, but it's still good, a very good benchmark. And it also enables us to train it on our own corpus. So I first have a function, process PubMed, that will start by taking out the irrelevant sections. So what I mean for that is that we're going to keep only abstract, introduction, methods, results, discussion, and take out things like conflict of interest, data availability statements. So this will be the first function we'll call on our full text. So for example, just to see that everything went well, length of our full text, approximately 1,700. If we look at the first element, it's still the table because it's like the raw data. And so once we do the process text, we'll have it in a character vector. So this is very fast. This is one publication. We also converted everything to lowercase. There were a few LaTeX artifacts sometimes, like use package. I also removed a few table references or things like that were sure not to work. But I wanted to keep, for example, some punctuation. For example, here, COVID-19, we have the dash in the middle. So we don't want to remove that. We can see there's also a few things like this that won't be useful, but we don't want to do too much sanitization because we risk taking out important stuff. So this is what our first step looks like. After that, we call prune text. So prune text will remove stop words. We can also use it to stem derivatives. So meaning we'll take out plurals. But so this takes a bit longer time. So in this demo, I'm not showing it. It's also good just for exploration. So it's stemming that I perform myself. It's quite basic, but a bit similarly as the sanitizing previously. We don't want to do too much because you can quite quickly come up to removing important terms, getting false things, Like if you just want to remove all the S, his would become high. So this is just an example, but so what I'm performing is basically I look a minimum number of characters. I think it's 4. I look if we already have the singular form. If we don't, we just keep the plural form. So this is for S, and I also do for IES to Y. So I'm not doing it here, but I'm explaining it still because it's something that I use it later that we won't see in the demo, but that I will talk a bit about. So we can wait a bit that it ends to prepare the print text. And I will also remove very rare terms that appear less than 3 times. So after that, we'll be able to call text-to-vec on it. This is a function I developed to wrap the call to glove-to-vec. There is a nice vignette that explains how to do it. This one will prepare everything to have a projection matrix. So we will have in rows our terms, and in columns the dimension of the glove embedding we chose. So here I chose 100. We'll be computing this after, and here I provided another intermediary file you could try to download. This Dropbox links. So if you use reget like this, save it as glovefit.rds, you should be able to load it with this. So you can try to do that. Okay, so the prune text function just returned. You can have a look. It's a bit hard to tell the difference like this, but you do notice there's a very few small words. There's no more of, the. These are the stop words. So once we have this, we can call the word-to-vec embedding. There's 10 iteration, 10 epochs, where the distance is gradually decreasing. Okay, so here we have the first epoch.
Would you mind saying what it's doing again? So is it generating a vector space, or what's it doing?
Yes, it's calling word-to-vec using the text-to-vec package, and it's building the embedding matrix. So approximately 30,000 words in rows and 100 dimensions in columns.
Cool, thank you.
So this is what I'm going to show in the tutorial, but we can start here with to have the results already. So once we have our embeddings, we can query each word. And so here I'm taking the example of EI, so emotional intelligence. So since it's the scientific publications, we have a lot of acronyms, so we can use these EI or any acronym that appears. So here we have the example. The most related term will be gratitude, and a lot of emotion and personal traits related. So as we want to understand a bit how our model was fitted to find clinically useful relationships, we first see that there is this global bias around the fact that, of course, we selected our corpus to be suicide relevant, but there's also scientific publication bias because a lot of terms will come back, such as significantly associated with. And so when we query using single words, we want to be able to find sets of words that don't always return the same bias words towards which the corpus is oriented. So because we want to find a diverse set of words that will be useful clinically. And so we can guide this discovery by thinking about what we're thinking we will find. So for example, medication, we would like to know what kind of medications are used. And so for that, the most related are psychotropic, antidepressant, antipsychotic. And also interestingly, pesticide appears. So this makes us understand that there's a bidirectional valence, meaning that it can be positive or negative. It can be towards the medication side or sort of anti-medication. Pesticide is used rather as a suicide mean in developing countries. So another set of words we're expecting to find, therapies. We have CBT, DBT, cognitive behavior therapy, dialectical behavior. And it also shows ART, which after exploration really refers both to art therapy and to antiretroviral therapy. So this shows the difficulty of NLP, natural language processing, because words can have ambiguous meanings. So the key point I want you to take out of this talk is about the vector operations. If you already heard a bit about word2vec, you maybe know the classic examples. There is the version with the king, the queen, and the man. But let's focus here on Paris minus France plus Germany. The idea is that since each word has a representation, so in our case, 100 vectors, 100, a dimension, 100 embedding. Each word is a vector of dimension 100. What we observe is that if we do Paris minus France plus Germany, so this is on general corpora, the word with highest similarity will be Berlin. So it's interesting because the algorithm successfully understood the relationships between these different concepts. But as I was digging a bit into this example, some talks or presentations around it were saying that also in the nearest neighbors, there can be other capitals, such as Moscow, etc. It's not only we get Berlin, it's especially that we are in a capitals subspace. And I thought that this would maybe be better to use in my exploration. So I tried to build up a similar query. And one idea I had was, since PTSD is mostly associated with military veterans, even though it can be also applied to survivors of abuse, but overall still significantly associated with military veterans. And there's this psychiatrist author, Bruno Bettelheim, that talked a bit about PTSD and ASD and autism spectrum disorder and autism in itself. So that's a bit how I got the idea of, well, maybe veterans, the link between veterans and PTSD is similar to the link between children and autism. I know it's maybe a bit crude, but we could argue that some symptoms are similar. And the results were quite good. If we do, for example, veterans minus PTSD plus ASD, we have these results on the right side. And what we see is that it's mostly socioeconomic terms. We'll have geographic terms, Iranian, Swedish. We'll have rural, indigenous, so more sort of geographic. We'll have also professionals, sort of occupation related, children, adults, age related. So for me, this is an evidence of a socioeconomic subspace of words. And we can revert it, PTSD minus veterans plus children. And here we have mostly psychiatric diagnosis. we'll have PTSD. Well, this was in our terms, but anxiety, psychotic, BPD for bipolar. So I think that this shows the evidence of the psychiatric diagnosis subspace. Okay, so our glove fit has finished now. NLP Embeds is a package I'm currently working on that's available on GitLab, but that there's no vignette yet. So it's very early version, but it will be expanded upon in the few months, in the next months. So we can do these operations. What I previously showed was the Shiny app I developed that was calling this function. So here is what I was saying about the bias words, beginning of exploration. This is a therapy query, medication query. So here I was starting to introduce the fact that we can do vector operations, but that they weren't very powerful. And here I was starting to talk about the concept subspaces. And so now we match back to where we were in the slides. Here I come back a bit on other vector operations I tried, because ultimately one of our key goals is to understand what people suffering from suicidal ideation, if we could find predictors on how, if they will, when they will attempt. And so this is some of my exploration to try to find what differentiates ideation and attempts. And we can see EI, emotional intelligence. This loops back to my first example. That is why I was showing it. And I think it's probably an important concept, even though it's kind of a not very well defined term. I think it conveys some meaning. Here there's the reverted. We can see that it's very different. So we need to explain a bit why. So once we perform this exploration, another subspace that seemed to be exhibited was a childhood adversity subspace linked to abuse, maltreatment. And a few terms I thought were quite important, but I couldn't really show evidence of a subspace. Are medical symptoms related? There was, for example, tinnitus, a few terms like these. Well, another thing I saw was, so neuroticism appeared when we queried schizophrenia, obsessive compulsive with autism. And so the first ones are more personality traits. And I was wondering if we can discover similar relationships for suicidal behavior, PTSD. So this is a more or less related research where the authors tried to do subtypes of obsessive compulsive disorder, and they first cluster on one scale, map it to a second scale after. So this concludes a bit the exploration part. So now we want to try the confirmation, because maybe the queries we entered don't really reflect the overall structure. Maybe we were just saying sort of a cognitive bias guiding us towards a bit what we already know. So this is when I wanted to try to make the process more automatic of discovering these groups of words. And I also wanted to see how they interrelate. For example, we saw that there was the therapies, the medications. Is there one that is closer to one diagnosis? And so how they connect. So for that, I thought about using density-based clustering. And so we can't use it on our whole 30,000 words. And so what I thought of doing is we first build up a list of clinically relevant terms. We build this list using the exploration we perform. So we have 23 operations, and each one will return 50 most closest words. So some words will be duplicated, and the unique words amounts to 800. So we have our matrix of 800 words by 100 dimensions, and we perform density-based clustering on that. So I wanted to introduce a bit the density-based clustering method. Okay, so for example, in density-based clustering, we can detect forms like this in our data set. And so this is using dbScan. We put a threshold on the density. But one of the limitations of dbScan is when you have, for example, two clouds of words, but in one cloud, there are subclouds. And so either you put a threshold that will detect the two large clouds, either too small, but you can't understand both. So this is where optics comes to play. This is the reachability plot from optics. The valleys show the clusters. And so here we can say this was our left cluster, and here are our subclusters that we previously couldn't find. So this is optics. And during my PhD, I developed opticskxi to be able to extract the clusters from the optics reachability plot. I believe HDBScan may be doing similar things. In my opticskxi package, I provide some functions to be able to compare various parameters. We don't know the number of clusters we're looking for, so that's one of the things we compare. This is the results on the first example on the shapes. So here is the example of the metrics that opticskxi uses to be able to say, okay, this is the best model. The clustering is best like this. So on the left, we have the different types of models. We had Manhattan distance. xi3 will determine the number of clusters. 0.20 is the density parameter. So this enables us to rank our models. And after that, we can show the optics reachability plots with our different clusterings and see how, and to be able to fine tune if we don't want to, if, for example, this one looks better or not. So. And last, we can come back to the original data, map the clusters, look at the discriminating features. Coming back to our data set. So we first build up our list of words, as I was saying, approximately 800. These are all what we selected. We subset our data matrix. And here we call the opticskxi pipeline. So this package is on CRAN since a long time, but I did add some new features. So a modified version. I remove, sometimes it's best to not have huge clusters, and also I integrated cosine similarity. So on this object, we can use the classic opticskxi functions as shown in the vignette. I'm just going to show them quickly, just show that it works. Up, the plot appears. So this next thing I wanted to talk about was nearest neighbors graph, because if we do a dimension reduction, classic PCA, ICA, t-SNE, on this data, it will be very overlapping, not very nice. We don't understand how the clusters interact. And so if we do a nearest neighbor graph, we can split things up a bit better. in my slides. Here is a huge graph with all the non-clustered words. This is the reachability plot. On the left, we have the psychiatric diagnosis. Here, we have the therapies, medications cluster. And the nearest neighbor graph look like this. Once we remove non-clustered words, we can simplify it again. So this enables us to explore. So one of the novel methodology is random vector operations. The idea is that we reuse the nice vector operations. We said that it's better to do like to find subspaces. And basically, I determine this based on the cluster. I determine automatic vector operations. So I redo the list of words, and when we chain it up to 10 passes, we find a cluster of serum-related, cytokines, proteins, neuroanatomical regions, and sleep-related cluster. So the cool results is that we discovered clusters we didn't really think about in the first place. And so quickly, the last minutes, I want to talk about evaluation. So how we're going to evaluate it is using databases of known relationships between diseases curated by clinicians. And one such publicly available dataset is PrimeKG. It's more bioinformatics focused rather than biomedical hospital, but it enables us to do, it's a good starting point. The core elements will be in our original text data. We replace our text strings by the identifiers that we have in our database. So saying ID 12 is related to ID 13. It can be, for example, schizophrenia is a mental disorder. So it's relationships like this, like parent-child. We compute the word embeddings using the identifiers. And we try to predict the known pairs. We generate random null pairs to have false positives and AUC performance measures. And the cool thing is, using this, we determine a cosine similarities threshold at, for example, 5% false positive. And once we have this threshold, we can say that all the terms above this similarity are related. And with that, we can build up a knowledge graph. This is the last thing I want to show. So one of my recent packages is sgraph. I just want to show my first results on kgraph package. This one is almost ready to be submitted. And this is the Shiny app that we're using at our lab. So we'll basically build us a knowledge graph like this. This is using the sgraph package that you can already use with on CRAN. It's a HTML widget. And so the knowledge graph will look something like this, putting related terms next to each other. The edges are proportional to their similarities. And so we tell what specific concept we want to learn about, and it shows all the related ones. And if we share several, we get the interactions between them. Maybe as a conclusion. So yeah, one of the results that come up is the importance of sleep. We shown some ways to integrate borderline clinically relevant concepts such as guilt, shame, and we put in evidence less well-known psychiatric diagnosis, dissociation, but also medical concepts, amusia, anhedonia. And now we're using it as input for our other projects. We basically have a set of 5,000 words, suicide related, that we will use on our AHR data analysis. And we are starting to use LLM pre-trained models, and we will try to compare them. So thanks a lot.
Thank you. That was a lovely presentation. I do work on addiction, and I love everything that you just showed. So I would like to take the methods that you've shown and apply them to the notes that are in our EMR. So I'd like to take the clinical notes for people who are coming in either with an addiction diagnosis or potentially with an addiction diagnosis, and try and understand what's going on in the word space. What I'm worried about is I have clinicians, and so I have clustering. So in the work you're showing, you're pulling in data from many journals, et cetera. How concerned would you be if there was clustering within the documents that you're trying this on?
So do you mean because it's done by several clinicians, and that each clinician has his own handwriting or style of writing?
Correct.
Yeah.
Correct. It would be style, and also because this is addiction, I'd be concerned that there would be subtle words used that were clues to avoid explicitly saying this person is using cocaine. But let's say there's 20 clinicians in the clinic. Each one might have their own slang for hiding cocaine or hiding cocaine use in patients. And any thoughts on just how badly that would mess with your methods?
It's quite a hard question. And I just started on the EHR data analysis, so I don't have too much experience yet on this. In suicide, we also have similar problems because the clinician will basically, like you said, avoid saying it explicitly. So we will face similar problematics, but I didn't really think about ways. That's the embedding is what we're trying to. I guess the embedding should make it work because we find relevant terms, so we'll need to build up a bit on it. But I think the embeddings is the good way forward for such slang, or it's not even slang, it's like really trying not to be explicit, but
right.
So I don't have any particular answer, but I think that embedding is definitely the way forward.
Thank you. It's a great answer. I knew it was an impossible question. I look forward to seeing what happens when you start to use these techniques within the EMRs, again, because I really wonder what's going to happen as a function of the number of clinicians. So lovely presentation, super valuable.
Thanks a lot.
I see one question in the chat. Are you able to see the chat?
Yes, I see it. So for beginners, I would suggest the text-to-vec vignette. So there are two. There one where first talks a bit about text processing, and one that focuses on glove word embeddings. So with this, you can start understanding how text-to-vec works, the tokenizer, the different parameters, creating the vocabulary. You will also have the parameters such as minimum frequency. So in this vignette, it talks a bit about how you build up your vocabulary. It also, here it shows using lasso It's sort of a prediction use case. And after that, you can go up to Word2Vec, the Word2Vec vignette. Here it talks about the term co-occurrence. The skipgrams window parameter will be the, as you move on your character vector, the skipgram window is the number of words in front and before you're looking at. So it's your word window. And so it's when words appear in this window that they are correlated. And Word2Vec basically makes this window slide and will tell you, oh, these two words appeared very frequently together in your window. So this parameter is quite important. Here we have the classic example of how you call the global vector, and this is the fit. So here the messages that you saw in my presentation. And basically my function wraps also these, and I just returned this object. And after he performs the word vectors, similarly as what I was doing, here is the sim2 function for cosine similarity. And I also integrated the ability to do subtractions. So yeah, he talks about Paris, France, and Germany also. I found a very nice presentation that talked about this capitals subspace, but I couldn't find it again. So maybe if anyone knows about it, you can put it in the chat. But I'll try to put it in my upcoming R packages.
Well, thank you so much. If there aren't other questions, I think we can end here. That was a great demo.
Thanks.